Hi, and welcome to part 1C of homework 2 for computational methods. In this homework, we're going to use the entropy function that we derived in part 1B, and we're going to maximize it and then show it that given a average and a standard deviation, it'll yield the normal distribution. Okay? So first thing we're going to need is we're going to need to import the minimize function. Okay, so now we have this minimization function. Then we're going to code in our entropy function from part 1b. Which is this function here. So it's the sum of the probability times the natural log of the probability multiplied by the number by n, which is the number of samples. So when we're doing this minimization, we don't care about the number of samples, the number of n, the number of data points, the number of students. We don't care about that because that's constant, so it doesn't affect our minimization at all. So what we want is we want the p times p dot log of p, and that should be natural log. Let's run that. Okay. So in this problem, we're assuming that we're giving it or are given both a mean and a standard deviation. So let me define the mean real quick. Okay, so how do we want to do this? So we want set this aside for now. Let's look at the minimize function. Let's just see what it wants. So it wants a function. It wants x sub naught, which is the initial guess of size n, where n is the number of independent variables. Okay. So then we're going to want so our function that we're going to be calling is going to be this entropy, and we're going to give it so entropy p, and we're gonna, it looks like it wants some sort of initial guess, so we'll have to define that in a second. And then this is where the constraints come in. Actually, okay, so I see. So then also we're going to need to put in constraints in here. And those constraints are going to be that our mean is our given, standard deviation is given, and that our p-value, the sum of all the probabilities, has to equal 1. So those are our three constraints that we're going to be looking for. Okay, so this mean is constraint 1. Okay, so for the mean, we're going to want to do probability times okay. So what this is saying, what we want to do is we want to sum up our probabilities at each interval, at each n, and the sum of the probabilities plus that should equal our mean, right? Then what we want to do is after we calculate the sum, the mean, we want to set that equal to our, well, so that should calculate our mean. That's what that function should do. Then what we're going to do is we want to define our standard deviation of p. Now for here, what we're going to need to do is I pulled up the standard deviation formula, which is this here. This starts with the square root. So np dot square root sum of okay. So now we need to multiply it by the number of samples. Yeah, so we'll need number of samples, which we'll just say is ns times np dot no. Okay, so looking at this formula, we need to sum up. So we multiply the probabilities times each number. So in our case, it'll be go from 0 to 10. So probability times each number minus the average. Square that. Okay. So np dot a range n minus the mean and then that, let's close that. Okay, so we have that, and then we're going to square this, divide by n at n sub s, let's make sure we got everything. So we have probability times should be everything. Actually, should call average is this. Okay, so those are our first two constraints. The third constraint is, let's call it p tot p. and we'll return np dot sum of p. Okay, so let's give our minimum guess, or our initial guess, which is just p dot full. And our initial guess is just going to be equal to the, yeah, let's do it this way. So our initial guess is just going to be equal to our, basically the probability, just evenly distributed. So what I mean by that is, if n is going to be 10, then our initial guess is going to be each probability is 0.1 for each of the intervals, and that way that gives the minimization function a place to start, which is reasonably close to what it might be, but we'll see what it ends up being. But that should, now we have to define what n is. So say n equals 10. So that just means our interval is 10. Then number of samples, so basically how many students we have, let's do 100. We have x sub 0, or x naught, that's our initial guess. And now what we need is we need to set our constraints. Let's see, it wants a dictionary here, so that's minus. Let's see, how does it want this set up? We want, so first one we need is type. We want equality. That's handy. That's where were we? Then we need to give it the function. And the first constraint is the mean. Okay. Let's do this again. I mean, standard deviation. And the third one is type. How do we set these equal to specific numbers? Saying is equal, we're saying these constraints equal to these functions. So that means that we have to put it here. Okay. So let's just say we want, if we're using our same example of the 10 grades spread over, that means we probably want, not this one, that one's fine the way it is. We probably want our average to be around 5. Probably want our standard deviation around 2. And this should equal 1. Okay, so we got those. Run this. Not happy. Is that how you do dictionaries? Okay, it's not reading any. It's not reading any constraints. It's not reading any constraints. Maybe I set up this dictionary wrong. So let's do normal bracket followed by the curly bracket. Change all these to curly guys. Now is it going to read those? Maybe that should be a colon, not colon. NP is not defined. Oh, forgot to run that. Can I get rid of that? It worked. No, it didn't work. All right. All right, so it's not happy with something. So it's not happy with either the log or the square root. Probably because those are too close to 0, huh? Okay, so it's hitting the iteration limit. So can we expand that? No options. I think that goes under options. Oh, let's give it a try. Okay, so I bumped up the iteration limit up to 1,000, and we're still hitting that limit. It looks like it's just kind of jumping straight to, well, so let's give it balance. That might help. Balance, how can we deal with that? Alright, we're still hitting our duration limit. So, just see something. Didn't work. Alright. Well, the only thing I can think to do is see if it tells us. Positive direct. So it looks like all of our values, aside from these two, are extraordinarily small. Oh, let's keep going. Still false. So, alright, so I took some time and dug around trying to find what was wrong and see if that would work. And what I found was that for these sums, or the mean and the standard deviation, I forgot to put the numpy prefix. So if I were to run all these again, ta-da, it worked. Why that made such a difference, I have no idea, but it worked. So now that we have this, terminated successfully, it's true. These are our probability values from 0 to 10. Well, from 1 to 10. Okay, so now what we're going to do is we're going to plot this so we can see a general shape of what it's going to look like. So we're going to do, oops, actually let's just copy and paste from the first start. Run that. Alright, so it's not happy with that. So let's do, so we want these values to equal our y. So we want res.x, and we want this to equal our np.a range n. Sweet. Okay, so we got this bar graph. And if we wanted to make it more clear, we could do dot add scatter. Use these same guys. Voila. So here's what we got. I think it goes from 0 to 9. Huh. Well, let's just update that real quick. Alright, so as you can see by this graph, which goes from 0 to 10, has an average of 5, standard deviation 2. So we can see by this graph, it's very, very similar to one of those normal distributions that I showed in part 1a. As you can see, it has that characteristic bell curve shape. And this line graph that I tried to show is even more clear. It even more clearly shows that bell curve. So what this tells us is that given a mean and a standard deviation, the kind of data distribution that has the highest entropy, aka it has the most information to be able to share, is one that falls along a normal distribution. So it falls along a normal distribution, and yeah. So thank you. That's it for part 1. So join me in the next video for part 2a of homework 2, where we dive into more optimization functions, specifically looking at the secant and Newton methods for finding the roots of functions. So join me then.